All right, so my name is Stefan, and I'm a PhD student at the National Observatory of Athens under supervision of Dr. Bonanos. Today I will talk about my analysis of evolved massive stars in the SMC and the LMC, but I will also talk about the group project that everyone on the team is working on, which is the HelAS project that was already introduced in the previous talk, in which we aim to address the role of episodic mass loss in evolved massive stars. All right, so like the title says, we are studying massive stars. Massive stars are stars with a mass greater than 8 solar masses that evolve on relatively short timescales and end their lives per definition in a supernova. Now, there's various reasons to study massive stars. First of all, because of the chemical enrichment that they provide, producing heavier elements that lower mass stars cannot produce. Also, they greatly contribute to the hydrogen ionizing fluxes in galaxies, and they dominate the momentum feedback with their supernova and strong stellar winds, providing feedback to the gas that the massive stars are embedded in. All right, so a massive star spends most of its life on the main sequence, burning hydrogen, but when it runs out of hydrogen in the core, it will evolve redwards in this Hertzsprung-Russell diagram. The evolution of massive stars is quite complex, but it is affected by a couple of physical factors. First of all, the initial mass, as you can see on the Hertzsprung-Russell diagram, different initial masses will evolve, or stars with different initial masses will evolve differently. So for a 9 to 25 solar mass star, you expect them to evolve to become red supergiants, but for more massive stars, you would expect them to become LBVs or Wolf-Rayet stars. Another important factor on the evolution of massive stars is the rotation, where if a star is more rapidly rotating, then the chemical fuel is mixed more efficiently, and this also alters the evolutionary track. And then a third one, which is the focus of the rest of the talk, is the type and the amount of mass loss, for the same reasons as the initial mass is also important. All right, so then moving on to the mass loss. So massive stars can lose mass in various channels. First of all, because they're so luminous, they lose a lot of mass in strong stellar winds, where basically matter is stripped off the surface of the star due to radiation pressure coming from below. Then there's also binary interactions, where if a star is in a binary, mass can be donated from one star onto the other star. But this is only applicable to binaries and not to single stars. And therefore, episodic mass loss may still be a dominant factor in the evolution of single stars. And then the third one is episodic mass loss, where in a very short time span, multiple solar masses are ejected from a system in a short outburst. And this is observed many times, for instance, in the Great Eruption of Eta Car. That's nicely shown by this HST image. And also other pre-supernova events where before the supernova, there was a series of outbursts where multiple solar masses were ejected. And this, of course, can alter the type of supernova and also the compact object left behind. However, we do see that this happens, but single star models continue to use a constant mass loss for the modeling, which can highly impact the evolution of stars, as we have seen that for a certain fraction of stars, these episodic outbursts happen. The problem, however, is that empirical statistics on the frequency, so the percentage of stars, but also the extent of the outburst is lacking. And also the theory on what exactly triggers these outbursts is very poorly understood. So this is where the HelAS project comes in. This is a 5-year project granted by the ERC with a 1-year extension due to the pandemic. So in short, the HelAS project will obtain about 1,000 spectra of dusty evolved stars in 25 nearby galaxies. Most of these stars have already been observed with the VLT, the FORCE-2 instrument, and the GTC, the OSIRIS instrument, and are being reduced as we speak. Once they are reduced, we will employ stellar atmosphere modeling and SED modeling to derive the parameters, like the effective temperature and the radius of the star, but also the mass loss to learn about the mass loss history of these stars. Then, once all the parameters are derived, we will compare with evolutionary models to compare the empirically derived parameters to what is expected for these kind of stars from theory, and this will help us to determine the role of episodic mass loss for massive stars and also the most massive stars. But today, for the rest of the talk, I will zoom in a little bit on my own work, where I have analyzed a small subsample of supergiants as sort of a pilot version for the HelAS project. So first of all, how were these stars selected for this subsample? So for the selection of stars, we mainly rely on infrared criteria, so the brightness and the colors in the infrared. We select stars from the Young et al. 2019 and 2021 LMC and SMC catalogs, which are foreground cleaned multi-wavelength catalogs with plenty of evolved stars to pick from. So for the criteria, which are shown in these CMDs, first of all, we require the sources to be bright in the infrared. So we apply a horizontal cut at a absolute magnitude of -8 in the 3.6 band, and then represented by the vertical cut, we require the J-3.6 color to be greater than 1 to mainly select the supergiant stars, like red supergiants, but also border cases like yellow supergiants, and dusty supergiant B bracket E stars can also be within these criteria. And these criteria come from the Bonanes et al. 2010 works. Then moving on to these CNDs, take a look at the bottom CNDs. As an additional criteria, we require the stars to be bright in the 24 micron band, as we are after dusty sources. And if a cool star loses a lot of mass, this will propagate outwards, and likely there's going to form dust around the star, and this dust will show up in the 24 micron band. So stars that are bright in the 24 micron band are likely very dusty sources and are very interesting for our purposes. So after applying these three criteria from these CMDs, we end up with 11 sources that we have observed. And these are represented by the colored triangles in these CMDs. And the black squares are supergiants from other works, just for comparison on where you would generally expect them, and see if the sources are more or less in the same location, or the sources that we selected are more or less in the same location. Okay, so we have observed these 11 targets with the MAGE spectrograph, which is a instrument mounted on the 6.5 meter Bade telescope. The spectra have a resolution of about 4,000, so medium resolution spectra, and the wavelength range covers almost the entire optical domain, which, zooming in on the red supergiants, is important because key diagnostics like the titanium oxide band and the calcium triplet are within this optical domain, which proved very valuable for the modeling that we will see a bit later. So for the rest of the talk, I will focus on these red supergiants. We have applied spectral classification criteria to classify the stars that we have observed. From the 11 stars, we have classified 8 as red supergiants. 1 was a yellow supergiant, not shown on the screen, and 1 was a supergiant B bracket E star, also not shown on the screen, as we will focus mainly on the modeling of the red supergiant stars. Okay, so for the spectral modeling, we have used MARCS models. The MARCS models are a set of atmospheric models that are 1D sampled spectra for cool stars. So we have constructed a 3D grid of these models with varying temperature, surface gravity, and extinction factors. And we have fixed the metallicity to SMC and LMC metallicity, and we fixed the mass of the models to 15 solar masses to cover the range in which you generally expect red supergiants to be. So we have constructed this grid of 3D models, and we start to try all the models we start to try to fit all the models to the spectrum. In this case, it's shown in black, is the observed spectrum, and the model is shown in red, basically overlapping the spectrum. So what we do is we calculate a reduced chi-squared for all the models on the grid and select the model with the best or the lowest reduced chi-squared and adopt this model as the best fit model. So for this particular star, we show the best fit model in the red. The best fit parameters are shown in the top left as sort of a ballpark, what you would expect for red supergiants. And the results for all the stars are shown in this preliminary table on the bottom. So for the chi-squared routine, we have done a bin-by-bin chi-squared fitting. That means that we compare the flux of the spectrum and the flux of the model in every bin and divide by the error and sum this over all the bins to compute a chi-squared for the entire spectrum, and then divide by the degrees of freedom to calculate the reduced chi-squared. Now, a couple of regions were excluded as my spectra were not corrected for tellurics. So they are contaminated by tellurics and the models do not contain tellurics. So excluding these regions is the only right way to do. So in these regions, we didn't do a bin by bin chi-squared calculation. All right, so this table is preliminary as we are still actively working on this and think about if the current approach is can be improved on or not. So from here on, we start to zoom out again because this is where my current work more or less stops on the modeling. For the near future, we have obtained follow-up spectroscopy, follow-up spectra in the infrared, and we aim to employ the same methodology on the infrared spectra as we did for the optical spectra. So again, we aim to employ the Marx models. We will aim to address the discrepancy found between measuring the temperature and the extinction from the opticals or from the titanium oxide bands and the temperature and the extinction measured from other parts of the SED, for instance, the infrared, as if you measure the temperature from these two different regions, there is a slight difference between the two, and we aim to address that. And another thing in the scope of the project, in the near future, we are going to derive the mass loss rate for these stars with SED modeling using Dusty. So again, when, like I said before, when a cool star loses a lot of mass, this will propagate outwards and we expect a lot of dust. And this has its own signature on the shape of the SED, where you expect a bump around 24 micron or in the middle infrared at least. And this can be nicely modeled with an SED fitting code like Dusty. And one of the crucial pieces of input for Dusty is the parameters of the central source, which we have derived in the previous step. So using my current work, we can then employ the SED modeling with Dusty to try to derive the mass loss rate, which is one of the key parameters that we are after. Okay, so coming back to the HelAS project, we have derived key parameters like the effective temperature and the surface gravity, and will derive shortly the mass loss rate. What we will then do is we retrieve the mass loss rate, what is expected for these stars from evolutionary theory, and see if the empirically derived mass loss rate that we find is similar or in agreement what is expected for these stars. If they are within agreement, then there is in principle no clues for episodic mass loss, but if they are in disagreement, then this could hint at a potential mass eruption that has recently happened or happened in the past, where clearly something has enhanced the empirical mass loss rate to be much higher than what we would expect. And in these cases, we need to reverse engineer the stars to calculate the extent of the outburst. So basically, we need to produce models that are capable of explaining the enhanced mass loss rate that we see. So in conclusion, I'm not sure exactly how I am with the time, but I will leave you with these three bullet points that capture the main thought process of the HelAS project. Thanks.
Thank you, Stefan. Are there any questions for Stefan? Any questions?
I have one question.
Go ahead.
Hi, Manos.
Hi, Stefan. Thanks for this very nice talk. One maybe a simple question that I have is, so you derive the stellar parameters from the optical spectra, and then the idea is to go towards Dusty, to go to the infrared spectra or SED.
Yes.
Is there are these two independent? So can you assume that the dust that is around does not play any role on the optical parameter assessment, and that then independently they can be the input to dusty?
Yeah, so I guess what you mean is the overall diminishing effect of the spectrum due to the dust that's surrounding the star. But this would show up in the extinction that we have derived, which is not necessarily input, I think, for dusty. So one crucial piece of input for dusty is the effective temperature, and I'm not sure if the surrounding dust has any influence on that, because the temperature is mainly derived from the depths of the titanium oxide bands, the relative depths. So I don't think that extinction by the dust will have influence on the temperature estimate, and therefore also not on what you would derive with or put into dusty.
Thank you.